In this video, we solve problem 11.2.102 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. The problem statement says a precast concrete wall is temporarily kept in its vertical position by ropes, see figure. And this is the figure approximately that we see in WebAssign. It says find the total force exerted on the pin at position A. The tensions in AB and AC are 350 pounds and 700 pounds, respectively. We're asked to round to 1 decimal place. Now, we don't have a coordinate system here, but it would be helpful to have a coordinate system so that we can represent the tension in this cable and the tension in this cable, not just in terms of their magnitudes as listed in the problem statement, but as vectors. When they're asking us to find the total force exerted, on the pin at position A, well, what they're asking is for that resultant force, the magnitude of that resultant force, when you add the tension in this cable to the tension in this cable. This is just a Physics 1 concept. Remember, the resultant force is just the sum of the forces acting on the object, and we've got 2 forces. So we need to add those 2 forces together. We're going to add them component by component once we get those 2 tensions in component form. Tensions are a form of force. And then once we have added those, we'll know the force, the resultant force at point A, and we'll have that in component form, and we can find the magnitude just using our formulas for magnitude. Okay, so in order to do that, we have to look here and superimpose a coordinate system. Now, you can put your coordinate system anywhere you want. You can put your origin anywhere where you want. I think I'm going to choose to put my origin right here. So my z-axis is going to go straight up from this. I'm going to make that my positive x-axis. And I'm going to make this my positive y-axis. Now, with this choice of origin, the point A is located at, well, we go 0 units in the x direction, right? Because we're not going backwards or forwards, we're staying on the y-axis. And we're going 10 feet in the y direction. And then we're not going up or down at all. So the location A can be represented as x equals 0, y equals 10, z equals 0. Now we need coordinates for the point B and the point C. The point B is right here. Now they tell us that this point A is 8 feet along this parallel direction. And this direction is supposed to be parallel to that. I don't think I did a very good job. I tried, but it's 8 feet in the positive x direction from that farthest edge of our concrete wall. So B is at x equals 8. We don't go in the y direction at all, so y equals 0. And z equals, well, the height of that piece, z is equal to 6. C has a z value of also equal to 6. We don't go in the y direction at all. Now, with this C location, given our choice of origin, we're going to have to infer the x coordinate here. This is 18 feet long, and then this is 8 feet. So if this is 18 feet and that's 8 feet, I know it's not to scale, but that piece on the other side has to be, what, 10 feet? And since it's behind the YZ plane, we're gonna have a negative 10 right there. Okay, so now that we have our A, B, and C, or the coordinates of A, B, and C, what we're going to do, again, because we're asked for the total force exerted on the pin at position A, is we're going to apply this fact from physics, that the resultant force is equal to the sum of all the forces acting at that location. And so we've basically got 2 forces over here. Those forces are the tension along this cable AC, and we know that that tension along that cable is 700 pounds in magnitude, and the direction can be inferred by this location, X or A and C. We can find the direction using the vector from A to C. And then we've got another tension over here, and that's 350 pounds. Okay, so we want to add that together with that, and we can't just add the two magnitudes together. Forces are vectors. So we need this force component by component, and this force component by component, or if you prefer, you can call them tensions. Forces or tension is a certain type of force, so they're the same thing. And then we'll add component by component to get the resultant force. So the next thing we need to do is find the tension in AC. It's our, we'll say our vector from A to C in component form. Well, the tension in AC has a magnitude of 700, so I can write that down. And the direction is given by the direction of the vector from A to C. So I'm going to take the vector AC, but if I multiply by that, unfortunately, it's going to have the same length as that distance in feet from this point A to that point C, and I don't want that. I want a tension, which is actually in pounds. So I need to take AC and I need to divide by its magnitude or its length. I'm thinking of this as a physical dimension, so I'm going to say the magnitude and the length are the same thing this time. And that's giving me the unit vector in this direction. And then I'm going to say, okay, once I have that unit vector, because it's taken the vector divided by its length, whatever length it was before, now it's 1 unit long after dividing by its length. When I take that and I multiply by 700, that's actually going to give me the tension that's pointing this way and has a magnitude of 700. I hope that makes sense. Okay, so take the unit vector in that direction and multiply by the magnitude. That's easy enough to do. To find the vector AC in component form, I'm going to take the coordinates of the point C, -10, 0, and 6, and then I'm going to subtract the coordinates of the point A. That's 0, 10, and 0. And then we're going to divide by the magnitude of this vector. And the way we do that is we take the components, we square them and add them and take the square root. So this ends up being -10. We're going to square that. And then we have -10 over here. We're going to square that. And we've got +6 there. So I've got -10 divided by this number, -10 divided by that number, and +6 divided by that number. And it looks like it's going to be the square root of 236, which happens to be 2 times the square root of 59. And of course, you could simplify. All right, and now we're going to do the same thing for the vector or the tension in AB here. Now, before I move on, a lot of students do get confused between this and this. They say, well, how can this be the magnitude? I thought that was the magnitude. And it's a fair point. It's a good point. This magnitude of the vector from A to C is actually a distance. It's sort of telling us the length of that cable. If I want to know what the length of that cable is, turns out that it's 5 times the square root of 59, which is approximately 15.36 feet long. That's how long our cable is in feet. But when I'm talking about the tension in the cable, I'm not talking about how long it is. I'm talking about a force in the cable, and we're using units of pounds for that. So what we need to do is we find this vector, which points negative 10 units in the x direction, negative 10 units in the y direction, and 6 units in the positive z direction from A to back to C. And those units are feet. And then we need to divide by its magnitude. We're going to take feet, divide by feet, and that's not going to have any units anymore. I don't know if you guys could hear that, but my washing machine just became unbalanced and it was just going crazy over there. I just needed to take care of that really quick. Okay, so we've got this unit vector, which is now unitless. We took feet and we divided by feet, so now it has no units, and then we multiply it by 700 pounds, and that's going to give us that tension. So the magnitude of the tension is 700 pounds. The length of the cable is that 5 times the square root of 59 feet. And that's why we have to divide by the magnitude and then multiply by a different magnitude, because this one's the length of the cable, and that's actually the magnitude of the force for the tension. Okay, so let's do the same thing for the tension through AB. Well, we know that that magnitude is 350 pounds. And then we just need to multiply by the vector from A to B and then divide by its length to get the unit vector in that direction. I'm going to take the coordinates of the point B, 806. And then I'll just subtract the coordinates of the point A, 0, 10, and 0. And then we'll take the components, we'll square them and add them and take the square root. Oops. And that's the length of that cable there. So we've got 64 plus 100 plus 36, and we take the square root. I don't think that simplifies it all. So it's just the square root of 203. Okay, now we want the force acting on this pin at A. So we're just going to take this force and add them together, and that's going to be the resultant force at A. Now, the way I've written it, I still have this scalar times a vector, and I've got a scalar times a vector divided by another scalar. It might be helpful to write all of these without these scalars out front. So I'm going to do that now. I've got the tension in the cable through AC is this, and I've got this 2 goes into 10 5 times. We've got 3 times there, and so we're going to have negative 3,500 over the square root of 59. Then we're going to have negative 3,500 again over the square root of 59. And then we'll have 2,100 over the square root of 59 right there. And then the tension through AB comes from doing something similar down here. So we get 350 times 8 is 2,800 over the square root of 203. 350 times negative 10, that just means we're going to add a 0. Then we've got 350 times 6, which is 2,100 over the square root of 203. And the total force acting on the point A, or at the pin A, is just the sum of the forces, the sum of those two tensions. And the way we get that is by adding component by component. So it's just going to be this plus this, times I hat, plus this times j hat, plus this times k hat. And I think I'll just pause this and write that down for you guys. Now, we were asked to find the total force exerted on the pin at position A. And that can be a little bit misleading, because you think, oh, if they're asking for a force, what they're probably asking for is a force in component form. That's not actually what they're asking for. They're asking for the magnitude of the force. In order to find that magnitude, we just need to take these components, square them and add them, and take the square root. But in order to do that, it would probably be easier if we had a decimal approximation for each of these guys. So I'm going to find a decimal approximation for each of these guys using my calculator. Okay, so I rounded to 2 decimal places. We're supposed to round our final answer to 1 decimal place. So I will do that by, well, first I'll calculate the magnitude of the force, which is what WebAssign is looking for, even though they asked the ambiguous question for the force. So I'll use approximately there. And of course, the way we find a magnitude is pretty simple. We take the components, we square them and add them, and take the square root. And when I do that, I get this, which is approximately 857.9 pounds. And I believe that is the answer that WebAssign is looking for. So all we did was we took these 2 tensions, we were given their magnitudes, and we wrote those tensions in component form. We said the resultant force is the sum of the forces. So we found these 2 guys in component form, we add them component by component, and then we found the magnitude of that force. And that is the total force exerted on the pin at position A.